Good morning, everyone. Welcome to One Concept Per Day portal. And the concept today that we are going to discuss is about the free body diagrams, forces, and power and energy. Okay, so most of the time we'll not be able to discuss only free body diagrams. Sometimes, it can extend to rotation also. In fact, this question is very much related to the rotation chapter. So you have something related to free body and as well as this one. Okay, let us start with this. This question is taken from May 2006 paper. This would be useful for a HL student. Right. The question is about the forces exerted on the supports of a bridge. State the conditions for the body to be in a translational and in a rotational equilibrium. It means he is asking you to find out what do you mean by translational equilibrium and what do you understand by rotational equilibrium. What is translational equilibrium? Translation equilibrium means when you have an object and you are applying a force, in every direction. You are applying a force like this, you are applying a force like this, you are applying a force like this over here, or maybe here, everywhere you are applying over here, but the object does not move. When does the object doesn't move? When the net force is equal to 0. Net force equal to 0. So you should write it as a translation equilibrium is an equilibrium wherein the net force acting on an object is equal to 0. Now, what do you mean by rotational equilibrium? Rotational equilibrium is one wherein you apply a force everywhere, but the object does not rotate. Okay, which means what do you mean by this? When will the object rotate? You would ask the question, when will the object rotate? The object will rotate only when there is an external torque given to the object. Now, if I have this object like this and I am applying a force here, see the object is now rotating like this. Object is like this. Okay. Now, let us say for example, if I am applying a force here, then what happens? So this is also applying like this. Both of them equal and opposite forces are rotating like this over here. But now let us say I am applying a force here. I keep this as a fulcrum and I apply two forces on the same side. Then what happens? You are applying a force here. This will make it to rotate like this. Okay, like this. Okay, while this object, if I apply a force here, okay, then this will rotate, make it to rotate like this. So in other words, it is like this. See, I have an object. I apply a force here. I apply a force here. It is pivoted over here. So you apply a force here. This will make it to rotate like this. This will make it to rotate like this. But the torque which this gives you, okay, if they cancel each other, then there is no rotation at all taking place. In other words, rotation means the total sum of all the torques equal to 0. I should write net torque acting on an object equal to 0. Then we get this as a rotational equilibrium. We'll just move on to the next one. A simple bridge consists of a rigid roadway supported at ends A and B. A tractor is in the position shown in the diagram below. A tractor is standing over here in a bridge over here. This is 2 meters, distance 1.8 meter between the two wheels. There is a normal force here at one edge. There is one more normal force at the other edge. The distance between them is 5 plus 2, 7 plus 1.8, 8.8 meters. Okay, and the weights that are acting are being shown over here downwards. The total load on the rear wheels of the tractor is 1.5 on the front wheels and 3.5 in the back wheels. Okay. On the rear wheels 1.5, rear wheels 1.5, and the front wheel it is 3.5. Distance between the rear and the front wheel is 1.8 meters. The rear wheels are 2 meters from A and front wheels are 5 meters from B. Okay, as described in the diagram. The vertical forces that supports A and B of the bridge due tractor are NA and NB respectively. State the value of the sum NA plus NB. Now here there are two types of equilibrium possible. One is translational. Which one is the system here? This is my system. This is my system. The bridge is my system. So it is not moving anywhere, nor it is rotating like this, right? So therefore, now what should I say for translational equilibrium? So translational equilibrium tells you this NA plus NB is equal to this force plus this force, right? What is this force? 3.5 plus 1.5 is 5 kilonewton. So NA plus NB should be equal to 1.5, 5 kilonewton. 5 kilonewton, which is 3.5 plus 1.1. Then determine the value of NA and B. Find the values of NA and NB. Now, how do we find this? Now, what we do is we will assume one of them to be a constant over here. Okay, so what we will do, we will consider maybe I will find out the moment about this point over here. Okay, when I will consider this is being pivoted over here. So when I do this, what will happen? So there is a force which is acting downwards. This will make this one to rotate like this. I can find out the clockwise moment in this direction. Okay, this is giving you clockwise. What is clockwise? What is anti-clockwise? Clockwise moment is nothing but which shows the torque in the form of a clock, motion of a hand in a clock. So you see, this is the way how one of the hands in a clock moves like this over here. And what is anti-clockwise? This is your clockwise moment, and your anti-clockwise moment would be like this over here. This is your AC. Now towards it. Now you see this is going like this. You apply a force over here. See, if this is my fulcrum, over here, you apply a force here, what will happen? It will now start rotating like this, right? So therefore, this is your clockwise moment. This is also a clockwise moment. This is your clockwise moment. But while this one, it's lifting upwards with respect to this, this will give you an anti-clockwise moment. Okay. Now, what is net torque equal to 0? Say, it says determine the value of NA and NB. So, you need to apply the torque over here because it's not moving. It's in a rotational equilibrium. That means the torque produced due to this is equal to sum of the torques produced due to these two torques. So, what should I do? I should say torque due to tau 1. This one is tau 1. Let us say torque due to this one is tau 2 and torque due to this is tau 3. Now, I can now write this as tau 3 is equal to tau 1 plus tau 2. This condition is satisfied because the bridge is not moving up and down, right? So therefore, what I will do is I will write this as what is tau 1? Tau 1 is equal to, what is the force here? 1.5 kilonewton multiplied by 2. 1.5 multiplied by 2, which should be equal to 1.5 multiplied by 2. I wrote it wrong here. 1.5 multiplied by 2, which is equal to 3 kilonewton meter. Okay. Now in a similar way, I will find out tau 2 also. What will be the value of tau 2? Tau 2 will be equal to 3.5 kilonewton, right? Kilonewton multiplied by, what is this total one? 3.8 meters. 3.8 meters. So how much will this be? Let us calculate that value. So I have 3.5 multiplied by 3.8 will be equal to 13.3. Will be 13.3 kilonewton meter. Now similarly, I want to get tau 3 also. Why tau 3? What is the value here? Say tau 3 is nothing but your ACK, which is anti-clockwise moment. Say tau 3 will be equal to this force NB multiplied by this distance. What is this distance? 5 plus 2, 7 plus 1.8, 8.8. So I should write this as equal to NB into 8.8 meters. Okay, I'll just write this as NB 8.8 meters. I'll write like this. But we have already said that here, if you look at this, we already said that since rotational equilibrium is seen, tau 3 equal to tau 1 plus tau 2. Okay, let us apply this rule over here and then try to solve it. So I will write this as tau 3 is equal to tau 1 plus tau 2, which should now be equal to NB into 8.8 is equal to 13.3 plus 3 should be 16.3. So NB should be equal to 16.3 divided by 8.8. What is this? 16.3 is kilonewton, right? Right, kilonewton. Now you see, I will not make any mistakes by doing this. Reason is because my unit I have already preserved. So always write the units whenever you solve any problem. Now let us solve this. I have 16.3 divided by 8.8. How much will this be? 16.3 divided by 8.8 will give me 1.85. 1.85 unit kilonewton. So what is the NA will be? NA will be equal to, now you see, this is your NA plus NB equal to 5 kilonewton, right? So therefore, this will be 5 minus 1.85, which will be equal to how much? 3.15 kilonewton. Okay, thus we have found out value of NA, NB, making use of the theorem of moments. Okay, I hope you understood this. So do like, share and subscribe to my channel for more updates. So we'll see the next problem in the next video. Thank you.